Another open method is the modified secant method. It's simply just a modification of the secant method in which we use backward difference for the derivative estimation. In this, so we have two initial guesses in secant method, and the researchers or developers said that, okay, instead of using two predictions, maybe we can have a perturbation approach. Rather than using two arbitrary values, we are using a fractional perturbation delta of the independent variable to estimate the derivative. What we mean is that we simply do this actually for the backward difference. Let's say f derivative x. Instead of using x minus 1 and xi minus 1 and xi, we will use xi plus a delta xi. So simply f xi plus delta xi. Again, this is a different value from fxi anyway. We will use this. Then actually in the fraction we will have xi plus delta xi minus xi, but xi's are cancelling out, so delta xi stays by itself. So this is the function that we want to use instead of using the actual backward difference. And if we substitute this into Newton-Raphson, remember that Newton-Raphson was xi plus 1 xi minus fxi divided by f prime xi. We just plug this into here. Then our modified secant method, let me write it with blue, xi plus 1 is equivalent to xi minus delta xi f xi divided by f xi plus delta xi minus f xi. So this is perfect. Now we have only one guess, just xi, and delta xi is simply a selection, and the choice of the proper value for delta is not automatic. If delta is too small, the method can be swamped by the round of error caused by the subtractive cancellation in the denominator. Here there is a subtractive cancellation. This shouldn't be too small, otherwise the subtraction will be 0 or near 0, and we mentioned that near 0 denominator value leads to divergence. So this is important. If it is too big, the technique can become inefficient and even divergent. So it shouldn't be also too big. However, if it is chosen correctly, it provides a nice alternative because only one initial guess is required. You can just keep the delta always the same, like for any problem. So you don't need to guess this. It's just a constant value. And the derivative approximated by forward difference approach. So derivative is approximated by forward difference approach. With this, because we have plus delta. So this is basically the forward difference we can think of. So this is good. Maybe this delta can be a normalized increase of xi, because if xi is changing, for example, 1, 2, 3 like that, this delta can be just 1. But if it is like in the hundreds, and if you try to change this 1 again, 100 and 101, the differences can be very near 0. The difference here can be near 0. Instead of that, we can have a normalized approach and try to normalize xi and get a delta, and unnormalize it to get a difference, let's say. So this can be an option. And this is good because, as we said, we will have only one estimation. In this slide, we will use the modified secant method to estimate the root of this function as an example, and this is example 6.8, and the delta value we want to use is 0.01, and the initial value is 1, and we know that the true root is this value. So here it is important to understand how we use this delta value. Simply, we want to find a delta x0, which can be found by actually multiplying x0 by delta, which means 1 times 0.01 is equivalent to 0.01. Then now we can use x1 is equivalent x0 is equivalent to 1, then the function value fx0 is minus 0.63212. We simply substituted this value into here and found this value. Similarly, we will use x0 plus delta x0, and delta x0 is just multiplication of this by x0, 0.01. Then f x0 plus delta x0 is equivalent to minus 0.64578. And let's use these in the formulation of the modified secant. x1 is equivalent to, first of all, x0, which is 1, minus here 0.01, the delta x, times minus 0.63212, that's the fx0, divided by minus 0.64578 minus 0.63212, and the result is 0.537263. And from here, the approximation error, the true error is simply 5.3%. So you can see we are approaching to the root with this modified secant, and this is the iteration 0. Now let's move on to iteration 1. For this, it's important again to get delta x value. Delta x1 is equivalent to, first of all, x1 times delta. So x1 we found it as this, 0.537263, and delta is the same again, 0.01. Then it is 0.00537263. Then we will use x0 as the delta, 0.537263, and not x0 but x1. This is x1 actually. Over here it's x1, this one, x1, and then x2 is actually x1 plus delta x1. So it becomes, so here we forgot to write 1.01. Here also it's summation of delta x1 and x1. So we sum this with this value over here, multiplied by 0.01. Or we simply multiply this by 0.01, we can say. So then this value is 0.5 54265. Then here we can find x2. I'm not going to write them all, just the result. X2 is basically 0.56701. Simply, actually, we are also calculating x1, which is minus 0.64578. You can calculate them, and this is then x1 plus delta x1 is equivalent to 0.038579. Actually, this is wrong. This value is 0.047083. You can use these in the secant method, modified secant method formulation, and get this x2 value. Then the epsilon t is here very small, 0.0236%. It's again the absolute. Then let's go to I equals 2. Then again delta x2 is equivalent to x2 times delta, which makes x2 is 0.56701 times delta is 0.01, and it's equivalent to 0.00567101. Then x1 is sorry, this is x2 now. x2 is 0.56701, and x2 plus delta x2 is simply summation of this with this. It becomes 0.572680. Then here fx2 is equivalent to 0.000. As you can see, the fx value actually is going to the 0, and we can validate with this because we calculate fx2 with the x2 value. In here also, fx2 plus delta x2 equals, here the value is minus 0.00867, and if we use these, x2 is equivalent to, sorry, x3 this time. You use the modified secant formulation here. The result is 0.567143, and epsilon t is, you can see that it's very small, 2.365 times 10 to the power minus 5%. So this is a good value for us. It's almost the same as the root value, the true root value here. You can see because the error is very small. And here, yeah, the important point is using this delta as multiply by x0. Be careful on this. We always multiply the predicted value by delta and add it to the predicted value and get the results. And you can continue if you want to, but this is a good value to stop.